Hello and welcome to this presentation on using ANSYS Workbench Mechanical, and we're going to look at using bonded contact with a beam formulation. This is not the usual or default option for setting up bonded contact, but it's occasionally useful. However, be aware of some of the settings involved and of consequences if there are temperatures applied to some of the bodies. Here's our model. We have a solid body here, and a line body moved right up against it. The two are not sharing any nodes. They're currently unaware of each other. Here's a look at the mesh, and this gives you an idea about the cross-section of this line body. It's acting as a beam in this model. We set up some simple forces and other loads on the model. We have a force out here on the tip of this line body, and a remote displacement applied to the back of this solid body. The remote displacement, note down here, has been set as deformable. That means it can thermally expand. However, on average it's going to be prevented against movements, and you can see that we've set no movement in X, Y, Z, and no rotations X, Y, Z. So it's held in space, but with this deformable behavior, it can thermally expand. Now, we have a thermal condition applied. We've put a 200-degree temperature in the solid body, but we have not applied it to the line body. With ordinary connections between a solid body and a line body like this, if for example we used a fixed joint, that temperature difference would not result in any thermal stresses. Now, let's go look at our contacts. There's just one, a bonded contact with the target as a face on the solid, and the contact as the vertex at the end of the line body. The formulation chosen here is beam. There are others. Some won't work with a line body to solid body connection, but beam will. What it's going to do is actually create a little spider web of small beams. It's reminiscent of the beam spiders used in finite element analysis decades ago. That small spider web of beams will attach the node at the vertex on this line body to nearby nodes on the solid body. When we specify a beam connection, what we're doing is getting beam 188 elements with a circular cross-section, and we're setting a radius value. We're also choosing the material, and that's from the materials available in your model. So it could be the same material as what's been used for these bodies in this simple model that offers only the structural steel. We set the radius. We don't get any view of what's going on. Let's go back to the mesh. How many nodes here are going to be attached to the end node on this beam by that little spider web of beam elements? That can be controlled with this trim tolerance number, and we've put in 10 millimeters. That's a radius. I'll center that crosshair on that vertex, and the circle shows the region over which nodes on the solid body will be attached. Let's turn the mesh on. It gives you an idea that we're going to capture just a few nodes. We might make that 10 value something bigger, but let's look at what happens. After we solve the model, if we go to Solution Information, we can click on Graphics, and you'll see images of constraint equations and images of that spider web of beams. This green is beams. This shows where it's attaching to the neighboring elements. The constraint equations are a result of this remote displacement. These little green beams are a result of the beam formulation for bonded contact. If we solve, there's our deformation, and we're getting thermal expansion in here, not just deflection due to that force. So most of what you're seeing in this example is thermal expansion, centered on the remote point here that controls the back face. Here's our state of stresses. They are localized where that beam spider is affecting the neighboring elements. Here's a plot, user-defined result. We put in BFE and that gives us temperatures. We can see the 200-degree temperature applied to the solid body. It does not give us any information on what's going on in beam elements. It's a restriction on user-defined results. Now we've put in some APDL commands. Let me blow them up. I turn on the ability to output graphic images. I set up a view. I show the element cross-sections. And I turn on contour coloring according to applied temperatures. Then I plot the elements. I also execute a solve command. And I do that, you would not normally do this, but I do it in order to get the temperatures visible in this element plot. And the reason I do that is that the temperatures are being applied by a table array, and it's not normally evaluated until a solve takes place. This will be followed by a second solve using the same loads, which wastes time and storage, but I'm trying to show you something here. This plot will be visible down in the post-processing area if other APDL commands have been entered. So we go down below and we see some more APDL commands. We make sure that we're showing graphics in the same way. We color now with element type numbers and select only the beam elements and plot. Then we select everything and we do a plot. This gives us our second two plots here. The first one comes from these APDL commands. Let's go see the result. There's our plot of temperatures. You'll notice that the solid body is at 200 degrees, while the ambient temperature exists out here in the line body. And look at the rainbow coloring in here. This is the beam Spiderweb, and those temperatures are transitioning from 200 down to the 22-degree temperature in the line body. These temperatures have been applied to nodes. And in here, I put in a BF list and a BFE list command to examine how temperatures have been applied to this model. If I go into Solution Information and scroll down, here we are. This is where the listing of temperatures starts. And you'll notice it's being put in at the node level. I scroll way down to where the listing of applied temperatures ends, and it notes that there are no element body forces to list. So no BFE commands were actually used in the background APDL batch run for this model. It was all done at the node level, and that's why temperatures changed from one end to the other end of these little beams used at the beam Spiderweb that connects things together. Now, these stresses are not being caused much by the force on the end. These stresses are a result of the beam Spiderweb not thermally expanding as much as the solid block. Here we see the beam elements in the model, and here we see the entire model, now with the temperatures not shown. We're simply coloring these elements according to element type. So there's a rapid once-over on the use of beam elements. If I was to apply this thermal condition to both bodies, let's just do that for the purpose of illustration. I want to select a body, click there. Now both bodies are receiving that higher temperature. Let's solve this model. There's our deformation. It's still a lot of thermal deformation. Here's the state of stresses. You'll notice the stresses are very small now. They're not being caused by a difference in temperatures. And you can see that everything is colored red in here. All these bodies are at 200 degrees. We don't see any blues. And as before, there are the beam elements. And there are all the elements, with their cross-sections thickened for viewing. Here we still see the 200 degrees. This user-defined result simply doesn't show the temperatures out here in the beam. So I hope that's been instructive. This method of connecting things together with the beam formulation is sometimes useful. Conceptually, it's easy to see what's happening. You do need to assign a material and put a radius on these little beam spider elements. You only get to see them in a plot like this to see what the cross-sections look like. And the other thing to be aware of is you do control how far out those beam elements go on the face by putting in a trim tolerance. Set up trim contact on, put in a tolerance value, look at the size of the circle and decide if it's big enough. Change the number if you like, and you might put in APDL commands like these from here down to here to give you an idea what's going on in a plot like this. Thank you for joining me.